Chapter 4 is dealing with the concept of torque, which is also known as moment. So the book is using moment. I usually use the word torque, but they're exactly the same thing. So they can be denoted as M for moment or T as torque. So I will be using this notation. But again, it's exactly the same as the M used by your book. Now the torque is defined as R cross F. Now R is a vector, F is a vector, so if you take the cross product between two vectors, you end up with a vector. Therefore, the torque is a vector. And remember, the property of a cross product is that this vector T must be perpendicular to both R and F, even though R and F are not perpendicular. Okay, now the big and one of the most important thing about torque is that it always depends from where you calculate it. Therefore, you always have to specify the point at which you calculate the torque. So if you have a point P, vector R, and a vector F, you're calculating the torque of F and R with respect to P, which means that you imagine that you have an axis going through P perpendicular to that page, and F cross R will give you a rotation, in this case, which is counterclockwise, and the torque will be perpendicular to both, therefore it will be inside or into the page. This is very different from a torque calculated from P prime, because in this case your vector R will be from your point P up to where the force is being applied. Now R prime in general is not R, therefore the value of your cross product will be different. So whenever you calculate the cross product, you always have to specify it with respect to which point you're going to calculate the torque. So I want to see that point. Writing this has no meaning. You need to specify from where you're going to calculate the torque. So point O, point P, whatever, but you need to specify it. So the nice thing about taking the torque is that since it's just a straight cross product, we know how to deal with it. You can set up the matrix. All you have to do is set up I, J, K, put your R vector, or X, or Y, or Z, put your F vector, Fx, Fy, Fz, and then just calculate the determinant of this matrix. And you end up with the torque. So when you're going to be dealing with 3D problem, I strongly suggest that you use this. If you're dealing with the 2D, then all you have is the same matrix but with 0 here and 0 there. Therefore, when you calculate the I component, you can end up with 0. When you calculate the J component, you end up with 0, or x at 0 minus 0 times of x, fx. And the only surviving term is going to be the k, which is just going to give you rx, fy minus fy, or y, fx. So in 2D, you don't have to set up the whole matrix. What we do and in 2 dimension is we set up a convention, which is that everything going counterclockwise is positive and everything going clockwise is negative. And this follows the same convention as we've seen before, the IJK convention. I cross J gives you K, J cross K gives you I, K cross I gives you J. So whenever you go towards the right, it's positive, and whenever you go towards the left, K cross J gives you minus I, J cross I gives you minus K. So if you have IJK, I cross J gives you the K vector. And this is assumed to be or positive. And whenever you do J cross I, so you're going clockwise, then you end up with minus K. That's where the minus sign comes from. So we're going to set up that convention. So in the case of a cross product, if you're taking R vector is here, F vector is here, you're calculating the torque about this point, R cross F will tend to rotate the system in the counterclockwise manner, therefore in this case it will be positive. If you apply a force F prime in this direction, then R cross F prime with respect to this point will tend to rotate the whole thing in the clockwise direction, therefore this torque will be negative. Okay, so for pragmatic point of view, the book is talking about the concept of the lever arm. I would like to show you how misleading that is and show you how to get around it. The lever arm is useful, but in some problems it will be totally useless. So let's see how we can understand why and how the lever arm concept come from. Let's imagine you have a vector r and you have a vector f, and you would like to take the cross product between r and f. Now remember by definition that if the torque is r cross f, if you want to get the magnitude of the torque, all you need to do is take the magnitude of r times the magnitude of f times the sine of the angle. And what the book does is it puts the sine and the r together and call this the lever arm, which reminds you of the fact that if you want to take the cross product between two vectors, the only component that actually produces the torque is the perpendicular component of f with respect to r. Okay, so let's imagine that you have your vector r and your vector f. What you can do is decompose your vector f into two components, f perpendicular and f parallel. Now you know that the only component of f that will give you the cross product is not this one, but the one perpendicular to the vector r. So really, to calculate the torque between r cross f, all you have to do is take the cross product between r and f perpendicular. Okay, because again the f parallel will not give you any value for the cross product between, because f parallel is actually parallel to r, and two vector being parallel will give you a zero cross product. Now what you can also do is, instead of decomposing the f vector, and you don't have the luxury of being able to decompose your f vector like we've done here, because you might not know this distance in your problem, then what you can do is play with the r vector and decompose the r vector into two vectors, one which is perpendicular to f and the other one being parallel to f. So if this is r, this will be called r perpendicular, this will be called r parallel. So we've done exactly the same way as here, except instead of decomposing the f vector as one perpendicular and one parallel to r, we're decomposing the r vector holding f fixed as r perpendicular to f and r parallel to f. So again, to calculate the cross product r cross f, all you have to do here is consider the r perpendicular to f, because the r parallel will not give you any value, and that's called the lever arm. So if you're able to know in the problem this component, then it's fine, you can use the lever arm idea. But if you're not able to calculate this, but the problem allows you to get this distance, then instead of decomposing the r vector and getting the lever arm concept, then just deal with the f vector, and it's not called the lever arm, it's not called anything, but it's as useful as using the lever arm concept. So in some problems you will not be able to use the lever arm concept because you won't be able to know this, or you could, but it might take you like 2 pages of algebra to obtain it, and it might just take 2 seconds to obtain the actual perpendicular component of the force. So remember that lever arm business, all they're doing is they're taking one of those two vectors and breaking it up so that you only keeps the perpendicular vector component. Now the lever arm does it with the r vector, but remember that you're not stuck in dealing with the r vector. You can do the same thing and take the force vector and decompose it into the perpendicular and component notation. And then just keep the perpendicular one. Okay, the book talks about a particular theorem, which is nothing else than if you're dealing with one force, you're gonna end up with one torque. Now you can do the same thing and generalize this idea as the torque being equal to the lever arm cross the sum of all the forces. So if you have not just one force dealing to deal with or acting on your object, but you have n forces, 3, 4, 5, you can just take the cross product of all those forces individually, and that will give you the sum of all the torques. And in many times that's what you want. This is called as known as the Varignon theorem. So you will end up using this theorem all the time, because in many cases you won't have just one force acting on your problem, but you're gonna have a bunch of them.